Hello, my name is Caleb Harris, and this is my report for Lab 4 for Physics 2211. The purpose of the Oscillations Lab was to examine the motion of a mass oscillating on a spring in an arc. The lab involved using a computational model to create an accurate representation of the energy principle. The main physics principles are Newton's second law of motion, the position update formula, the impulse equation, and the first law of thermodynamics. The momentum equation, momentum equals mass times change of velocity, and the impulse equation, mass times change of velocity equals force net times delta t, tie directly to the kinematic equation, v is equal to v naught plus acceleration times time. Vf is the final velocity in meters per second, while v naught is initial velocity also in meters per second. A represents acceleration in meters per second squared, and t represents time in seconds. The position update formula is final position is equal to initial position plus v average times delta t, and is used when net force is not constant, like in spring or orbit problems. The first law of thermodynamics is a principle of nature stating that energy is never lost or gained, only changed. The equation is delta E is equal to change in kinetic energy plus change in potential energy plus change in spring energy. This equation can change depending on the system and the surroundings. Finally, Newton's second law of motion also plays a role, which is represented by the equation F is equal to mass times acceleration. F is force in newtons, and m is mass in kilograms. The main result of the lab was that the computational model was similar to the experimental data, and that it accurately depicted the motion of the spring mass system. The model accurately depicted no change in energy. The system consisted of a mass attached to the spring, and the surroundings are everything else in the universe. The mass starts from a position of negative 0.101 meters in the x dimension, negative 0.636 meters in the y dimension, and 0 meters in the z dimension. The mass starts with a velocity of 0.0021 meters per second in the x dimension, negative 0.00208 meters per second in the y dimension, and 0 meters per second in the z dimension. I started the coding by editing the initial position, initial velocity, spring constant, and relaxed length given to us in the production video. Using the spring force formula, I added code to calculate the magnitude and direction of the change of position of the mass attached to the spring. Then, using the law of conservation of energy, I edited the equations to calculate the system's kinetic, gravitational potential, and spring energy. The next part of the code involved the momentum principle. First, I had to calculate the net force by summing gravity and the spring force. I used that value to update the object's velocity using the impulse equation. With that velocity, I was able to use the position update formula to find the new position of the ball after each time step. Finally, I had to write the code for the energy changes, which was just the final quantities of the energies minus the initial quantities of the energies. According to the law of conservation of energy, the sum of the kinetic energy, gravitational potential energy, and spring energy, the total energy of the system. I used the principle to write in an equation for the total energy and then the energy change. The main similarity between the model and my data was the sinusoidal shape. Both graphs accurately show the effects of springs on an object's motion. The main differences were the starting points and the maximum points of the graphs. In the x position, the experimental data reached further positive and negative positions than the model. In the y position, not only did the model start from negative 0.64 meters, experiment data started from negative 0.723 meters, but the model reached further positive and negative positions than the experiment. The possible sources of error are that the hand might have enacted a force on the object, and that the net force calculation ignores air resistance. The energy principle is satisfied by my model system. The change of energy in my system is zero, and the graph supports this since delta E stays on the x-axis. To calculate the period of oscillations, I took the average of the periods. For the x position, the period is 1.168 seconds. For the y position, the period is 1.3 seconds. The period in the y dimension is greater than the period in the x dimension. This means that on average, it took the mass longer to reach back to its original y position than its original x position. The computational model was similar to my experiment. This lab explored the momentum principle, the first law of thermodynamics, Newton's second law of motion, and the position update formula.